Hello out there, and welcome to the No Shit Cast. I'm your host, Matt Frazier. Woo, got him back on, ladies and gentlemen. Mr. Neil Thomp is joining us on the show tonight. Going to have us a fun, topical discussion. Kind of got this set up with my partner here, the Grey Wizard of Historical Knowledge himself, Mr. Eric Smith. He's joining me on the show tonight. How you doing tonight, buddy?
Like a man that really knows where his towel is at.
Hitchhiker's Guide to the Galaxy?
That's the reference.
I was just checking. I wanted to do this because one of the things, Eric and I, especially Eric, have been having a lot of questions. We've been seeing a lot of interest in this electric universe theory stuff. And I got the guy that sort of kicked me off in all of this. Mr. Neil Thompson's on the line with me. How you doing tonight, Neil?
I am doing well. Thank you very much.
Man, I really appreciate you, sort of answering the call here, bud, and kind of coming in and being willing to deal with, filling in some of these potholes that we sort of have in our understanding. But I know, look, I'm of the two, I'm the stupid one. Okay, let's be clear. All right. So,
okay.
It's one of those.
So I'm going to be dealing with the erudite situations. Eh?
So I'm hoping that I don't drag the conversation down too much, but I want to really let you guys kind of have an open discussion back and forth about, these theories and the way that they fit into physics and sort of how they change. What is the paradigm change that this really presents? So I'll make the introductions here. Eric, you want to kick this off with anything specific, or do we want to let Neil? Well, Neil's the guest. We'll let him sort of start off here.
Okay.
Okay.
Yeah, you were interested. You were saying you wanted to talk to Eric probably a little bit.
Well, I was just going to ask what Eric's background was. How do you approach this, or where do you approach the model from, or the paradigm from? Because each person sees what they see. They come to it because it answers something that they usually can't find anywhere else. And in my opinion, that's usually the sign that a lot of things are coalescing. Now, it could also be a sign that people are throwing their money away into something that's foolish too. So
right.
let's not pretend that there isn't arguments against. So
sure.
But what's your general background? Mine, I'm an engineer by trade, engineering tradesman. So.
Gotcha. Well, I have a bachelor's in history, a minor in philosophy, and I graduated last December 15th. Plan on going to get my master's. I've got a good GPA and like 6 letters of recommendation from my professors and that sort of thing. I also professionally write and produce music. And I have a big history in being interested in science and metaphysics and things of that nature. The way that I approach this subject is that I don't know much about it. I know what the standard model of science says, like what you can go out and read textbooks on in science, or books that you might get at the store that's not textbooks, that's written by scientists, and of course documentaries that you would see on TV and things of that nature.
And let's be right up front that from this point, I have no argument. I was there too, and in almost all those science books, and history books, there are a few enigmas, but generally they're doing good work and they're doing scientific work. So I'm not here to deride. I know there's a tendency to laugh at the old paradigm, like we mock flat earthers.
Gotcha.
We mock those who think that the earth is the center of the universe. Those type of things. Mock worthy, some might say. But that's not really the truth of what these people are doing. A lot of them are doing very scientific things.
Sure.
The trouble becomes what this framework hangs on. And that used to be something you could ask in the 1800s. And we simply don't ask the question anymore. The natural philosophers died off. They're gone. There's no one there to make money in that field. And we thought that we had solved everything. Obviously, we didn't, but that's our hubris, right? So
Sure. And basically, that's my background and my approach is that I have a fairly good grasp of what gravity plays a role in terms of science today, and I'm curious how the electric universe theory supplements or supplants that.
Actually, well, let's look at it then from your point of view. Do you know the history of Newton and so forth?
Yes, sir.
Okay. And he was like sort of dabbled, I wouldn't say dabbled, or he...
in alchemy?
Alchemy, yeah.
Yes, I know that.
And the argument, of course, is that his pissy fights with intellectuals across mail and in front of the courts of the world was recorded and
Yes.
became legendary.
Yes.
And why we know of them.
Like the story of how he invented calculus to win a bet that he made in a tavern.
You're getting it. See, I'm when I didn't completely finish university. I went into college because I wanted to learn electrical engineering. The university is, of course, not hands-on, and the hands-on is clearly where you want to be. You want to experience these forces for yourself, and know why you can't do what you think you can do. Why free energy is not a thing, but what is the right-hand rule? Those type of things. Like how you can watch it. You can, and it's very hard because let's be honest, it's one of the few engineering disciplines which everything you work with is invisible.
Right.
You don't really know. You don't see the electricity traveling anything. You can't tell if a circuit is on or off by looking at it. However, that said, from your point of view, or coming in from that angle, he famously stated something that I 100% agree with, and he was being very honest, where he said, "I frame no hypothesis." He does not know what causes gravity, and he was very honest about that.
Speaking of Newton, right?
Yes.
Yes.
Sorry.
No, I'm just making sure.
And that right there is the big question of the day.
I would submit that I don't know what gravity is, and that science doesn't know what gravity is, and that at least
you're being very honest.
What I call science doesn't know what it is, right?
But, no. The science is always the same. You don't understand. I don't want to be saying that there's a different science or anything, because that's also not true.
Okay.
Then aspect.
Science.
No. I just want to be very clear. Then
sure.
Because I'm laying it out for the viewer and everything else. Science to me is the Richard Feynman aspect of where he goes, we take a guess regarding nature, we do the numbers, and then we compare it to reality. And if it isn't, it's wrong. It doesn't matter what your name is, doesn't matter what school you went to.
And you're talking about Feynman of the Feynman diagram, right? Right.
Richard Feynman. And the quote is just basically a little 60 seconds on science, but basically I summed it up very nicely. But the aspect is that it's falsification. You're always wrong. You're always not wrong yet. You see, there's always a better explanation going out there that can answer more anomalies that you might have missed, and that just aspects to your theory. Like electrical engineering is basically combinations and utilizations of the rules of Maxwell, just those 4 rules. But that's not really, when you get right down to it, we look what we do with it. There's a lot more there than you don't really see if you start placing things in different orders, different capacitances, and how you would make circuits and so forth, and then playing that game. But that's really the difference is that he was being honest there, and that is the big question: what is gravity? And there's this answer that seems to say that basically that gravity is a bending of space and time. Now, of course, the faster you go in light speed, apparently in this theory, the more your mass increases. Well, that does seem to be the case. The E equals mc squared does seem to be true.
Right.
But the evidence, that's not really that's often given as some sort of like law of relativity or something. It isn't, obviously. It's just, it's used in nuclear reactors. So it's we basically calculate how much mass something has lost. The interesting point is that what is mass? How do you lose it? Like, this is another big question. So really, the fundamental basics that we call things, that we give numbers to, like even time itself, are just man-made constructs in many ways. So.
Well, I wouldn't say that mass is a man-made construct necessarily.
No. I meant that we apply numbers to it. I'm sorry. I did want to be clear on that we calculate its density and blah, 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 via that, and we can give its mass.
So I was hoping that you could speak to some specifics and stuff too. There's a lot of, when you touched upon Einstein's relativistic ideas, right? About
I'm just staying within the framework that right now. So, okay, but I'm not really opening. I'm going to open the can of worms. I'm just being careful on what point of view that you want to explore. So,
okay. Well, I was hoping that you could describe some specific ways in which the electric universe theory addresses some of the things that relativity addresses.
That's a good one.
Like, for instance, as examples, we're able to see a lot of experiments that's been done, like the one in 1919 where they were able to see that stars were positioned beside the sun when they were taking a telescope picture of the sun during an eclipse in 1919. They were able to see that the stars that were previously on star charts had basically moved, and that they had moved the amount that was predicted by relativity. And the prediction was that the mass of the sun, because of the gravity of the sun, it warps the space-time continuum, and it would warp it in a particular way that would match gravity, and that causes the bending of light. This was evidenced in 1919, which is one of the backbones of the theory of relativity.
Is that what they call the lensing effect? Is that part of the same?
That's part
sort
of that,
idea?
yeah.
Okay.
And also, I was wondering if you could address things like time dilation. You had mentioned how when you travel faster, you gain and or lose mass, right? And you also have time slow down for you. The faster you go, the slower time passes for you in particular. The closer you are to a gravity well, the slower time goes to you as an individual, right? So this is how particles who have half-lives that wouldn't allow them to go from the outside of our atmosphere down to the surface of the planet make it all the way down to the surface of a planet and are able to be viewed in a cloud chamber because time dilation, they're moving so fast, their half-life extends out to the length of time that allows them to actually reach the surface of the Earth. This process is another one of those big proofs and experiments that shows that there is a relativistic idea that gravity exists and that it warps space and time and it bends light and that it also warps gravity because the continuum is the space-time continuum. So as it warps, it also slows down gravity. And I was wondering if, and there's some other questions I have too about singularities.
This is a good one right here. So let me just start with your first one. That's Eddington, and it was, if I'm not mistaken, somewhere around April or May, and for some reason, like the 19th, but it's still 1919, so I don't want to think it was the 19th.
Okay,
anyway,
wait, which one was you talking about? That was the first one. Which one? What are we?
This is your event in 1919.
Question. Yeah, which was
your first question, which was regarding Eddington and the experiment. Or the lensing effect and the movement of the stars with regards to
all right. Just making
surface
sure.
of the sun because it was an eclipse at the time.
Okay, go ahead.
Yeah, and that's why he went out to this time.
Yes.
Now, I think that was basically the beginning of the end of not only natural philosophy, but it also fractured science, and we have not advanced since that point.
Now, can you clarify that statement? Because I don't understand that statement. It would seem to me that that was almost the beginning of modern science and the division between Newtonian physics and relativistic viewpoints, and that from that point on, we were able to capitalize off of that those two papers that Einstein wrote, and was able to do all sorts of things. Like, so could you clarify that statement?
Well, I don't think that we could do. I mean, it's not. I mean, these theories haven't lent to as much confirmation as you might think.
In what sense?
I'm not really saying. I'm going to go very clearly, though. I'm going to explain it to you. So, the first one is the 1919 experiment. So, he went out to an island and he took a telescope and he aimed it at the sun, and of course during the eclipse, and they were measuring the stars. Now that was one experiment, but that was apparently enough. Now there was movement of the stars, enough for him to write a book on it.
I see.
Called The Internal Constitution of the Stars, which came out in 1926, and it's basically the Bible in which all of cosmology has laid its hand on since then. He was trying to maintain relevance in a time when he was becoming irrelevant. Now, he rode with with Einstein, and he's the one who made Einstein the crowning jewel that he is.
And you're talking about like the
Eddington himself, Sir Arthur Eddington,
the astronomer.
Yes. So, because of where he was in his life at this time, this was basically his chance. And he took it.
Yes.
Now, I don't think that he did see movement of the stars, and we do as well. The trouble is that if you, there's a certain other doctor by the name of Dr. Ed Dowdey from NASA who has come up and flatly said that this is an incorrect theory. And he lays it out very
relativity
accurate. Yeah, okay. No, this particular lensing effect, and he explains it very clearly.
But that's a part of relativity, though.
No, I'm just going with the experiment itself and what it means, because he's basically saying the issue is that the lensing is not happening far enough away from these bodies, especially the massive ones, that it should be happening. In fact, we should be seeing a lot more lensing than we currently do. Now, the reason that we're not is because we're seeing, and this is, of course, he measures it with, and it's much closer to the surface of these structures. And it basically implies that we are seeing the atmosphere density change, or the atmosphere around a sun. And just like it does around the Earth, the sun actually comes up 8 minutes after we see sunrise, or 3 minutes or something, because of the atmospheric bending.
It's 8 minutes because it's 94 million miles, which is an astronomical unit.
No. I don't mean the actual time to light to move.
Okay.
I meant that the sunrise looks weird and flat, and so does the sunset, because of atmospheric lensing. That the sun actually comes closer as it gets, like it speeds down quicker than it does, because there's actually starts bending as it gets closer to the surface
I know what you're saying,
planet.
through the atmosphere of our atmosphere.
Through the atmosphere, yes.
Right.
And it starts getting redder, of course. Now, that's obvious. It seems pretty obvious to you. You understand this. So this is an atmospheric and optical effect. He's saying the same thing is happening around galaxies, and this is why we're seeing what we're seeing. That's just, and now, in addition to this argument, he laid down several other very obvious proofs to it. Number one, we see, for example, a lot of what's called Einstein rings, but a lot of them, in fact, most of them are blue. And the reason that they're blue is because blue light bends more.
Okay, can we go back to some of the things that you said and address those issues?
Sure.
Okay, just so for my clarification, okay?
Of course.
Because when you talk about the lensing effect happening closer to or away, and it should be closer, Like, I don't understand what you meant when you said that, because the lensing.
Basically, the distance between the angles, there should be more lensing than we actually see, because the effect of gravity should be further away than these bodies.
He's saying,
Plus,
it dissipates way too fast. If that's is what he's the way I'm interpreting this,
it's
is
not
that this
reaching
guy
out as far as it should.
Yeah, it should actually. It shouldn't dissipate and disappear so quick, so close to the surface.
What dissipate?
The actual lensing effect. It should go further. If those large bodies, those large masses, this is what he said, right? If those large masses are causing that, right, then that lensing effect should also it should definitely diminish as you go further away from the mass.
No, that's not true.
No, I'm telling you that's what this guy's saying.
Yeah, that's what. See, this is what I'm asking, though. This is what I'm saying, right? That description of the lensing effect is not how I understand the lensing effect. I mean, as an example, I guess would be to say that.
But you can understand. You can understand when a physicist wants to graphically show you or physically show you the effects of gravity on a massive object. They take a great big sheet, they stretch it over like a drum, and they drop a bowling ball in it to show you how it funnels gravity. Wells funnel into mass.
Yeah, I understand that.
That's how I learned it. I remember in school.
That's why I can see like someone saying, "Well, then you should see the effects of that gravity well much further." It's like it comes in and goes straight down. Right, that's the where is that? Where is that?
It's not actually as far as it should be.
That's
it's
what they
basically 1/3 or less than it should be.
Okay,
that's what this NASA guy's positing, though, is right. That you should be able to see it, but where is it?
Okay, but
in addition to that, he indicates that the Einstein rings are likely blue because blue light bends more, and this is why we're seeing a predominance of these blue Einstein rings. Now that's just the lensing question itself.
But the lensing effect is showing stars moving because of the warping of space-time by the mass of the sun, and they move. Huh?
No, we're seeing stars move, but we're having a debate on the mechanism in which they're happening. One is he's arguing that it's atmospheric lensing, and the other is arguing gravity.
Right.
You pointed out, Eric, though, that they predicted where they were going to lens to, and then subsequently measured that.
Yeah,
right?
yeah.
So then they must have had some sort of understanding of the predictive quality of that lensing effect before they made the prediction.
Yeah, I mean, they took into account the atmosphere through which they were taking the picture. They took that into account into the mathematics, right? So
the atmosphere of the sun?
No,
there's no atmosphere connected to the sun. The sun doesn't have an atmosphere.
There is.
I've never heard that.
The sun actually has a fantastically amazing atmosphere, 3,000 miles thick, and the coma gets much more dense closer to it. And that coma is actually the footprint of another effect altogether, which is this is where
wait a minute. You might have to back up and explain how the sun has an atmosphere. I mean, the sun has a corona, and it has
that is an atmosphere, yes.
Yeah, but like an atmosphere, like with gases that are not on fire, like air, oxygen,
there's nothing
carbon dioxide
on the sun that isn't ionized fully, and there's not really it's not really a fire per se. I mean, obviously it looks like one.
Okay,
but
yeah,
it's an electrical effect. It's more like the charge glow around a particular anode.
They didn't take pictures of stars through the sun's atmosphere or the sun's corona or the sun's solar wind or anything of that nature. They took pictures of stars that were behind the sun to the right of it, like not in its atmosphere or its corona or anything like that.
What they did is they were using the moon as a blocker at the time.
Yeah, so that they could see the stars
they only
around it.
They only had that short period of time.
Right.
Now, the reason I'm not trying to say that the people today are not doing amazing work. I'm saying that
today they use lasers to compensate for the atmosphere, our atmosphere. Today they shoot lasers into our atmosphere, and they gain an actual molecular density of the atmosphere, which they're able to calculate out of the focus directly. But this is based.
I love that. That's a very wonderful technology.
This is based on the mathematics, though, that they used in 1919 to compensate for the Earth's atmosphere. So I
don't really think that that's the case, though. I don't think that is exactly what he did back then. We got to understand how primitive they're really dealing with here. I mean, we also got to give credit for the fact that I'm not trying to completely diss Einstein, because Einstein himself.
No, I'm just trying to figure out how the electric universe theory addresses the same thing, right? Like there's an explanation from a scientific standpoint, and there would be from a universal electric universe theory standpoint, I would imagine.
Well,
right?
I would say it's the same. The argument becomes, what is causing what you're seeing? That is the argument.
Right.
Now, the density of galaxies and the density of what we're seeing, and as you probably already know, you've heard of these like dark matter chains and stuff like that, because they're starting to see these things as they get better and better telescopes as technology advances. I mean, we can do. I mean, just since since Hubble went out.
Are we going to talk about galaxies now? Is that where we move?
No, I was simply, that's one of the things that lensing happens around.
Well, it happens around. It happens around all kinds of things and stuff. I guess that's what I'm trying to say is, anytime that stars have to pass through some gravitational well, they bend around it because the space-time is warped, and light only knows a straight line.
Is that really the case? Is it simply, is space-time really warping? What is space-time?
Can I ask
how can we possibly say it's warping if we don't even know what it is?
Can I ask a question?
Because we see it bending.
Time out. Let me ask a question. Okay.
Well, this is the paradigm right there, right? See?
I'm loving this, by the way. This is.
Oh yeah. I'm not upset or nothing, so don't feel that I am. I hope that you don't feel that I'm being antagonistic or anything. I'm just trying to get some straight, answers to questions.
I also understand that we don't necessarily understand. Like I can't possibly nail down every single thing that you possibly know.
Well, I'm just saying that's just about the sun. I mean, we could talk about the time dilation. We could also talk about some other questions that they bring up. Go ahead, Matt. I'm sorry.
I still got a question.
Matt, please go ahead. Yes.
This is how you know we're having fun.
Is it possible, Neil? Then, because I struggle with this too. Okay, but you're not saying that the things that Eric is citing are not happening. There's nobody denying that what's being seen is big.
In the least.
So is what you guys are saying then that there's a misattribution of portions of the aspects of what we're seeing, or that it's the entire reason we think we're seeing it is wrong? Like, is this a piece of a puzzle?
Are you asking me or him?
I'm asking Neil.
Okay.
Like, do you think maybe?
I think this is a piece, because basically you get data back from a satellite or a telescope, sometimes minuscule amounts of data, or sometimes fantastic amounts of data, which you cobble together using what you think your theory is, and you see what you think you're supposed to see. Now, admittedly, that's still an amazing piece of data analysis and work. And the fact that none of the Electric Universe guys, are ever going to launch a telescope or a satellite into space. So we have to use the data that we come across. And the data should be considered, generally speaking, sacrosanct. No one's going to deny that the data is there. So, but the question is, why does it happen? And the inference that's basically never going back and challenging your assumptions. See, and we have to go back and challenge why we think that is, and what lead us to think that was the case. And the issue then being, if this gentleman, who is, he works for NASA, and he actually said, look, this is an optical effect. We're not seeing it nearly as much as we do. This would imply then that the idea that space-time is causing this is incorrect. So if space-time isn't bending, we have to understand what Star Trek did to us.
But something is, right?
Time, we have to understand that it sort of had a hold on us. And as much as I love it, we also have to look at what do we really do with high-powered machines? How do we really affect the world?
Yeah, but all right. So the lensing. I mean, what you're saying is that you're not denying that it's happening. You're saying that it's not happening for
Same reason it's happening. Yeah.
It's not happening for entirely the same reason. Like, you're not saying gravitational lensing doesn't exist. You're saying that it's not this. It's not the. It's being miscredited or giving too much credit for the situation, right?
Yeah, it's not. I don't think that gravitational lensing itself is a thing, as a gravity lensing, like the two words. But the effect that we see in space, I am not denying. I am saying that it is optical, and I agree with the gentleman's assessment of it. And the reason that I agree with it, because it generally fits with everything else that I've been seeing here.
But it's measurable and predictable, though. You're accepting that there's math that says that this shit exists, and here's how you can predict it, and that's where it should be.
Well, we only have the pictures of space, and what we've done with them,
right?
And as the moon goes around and stuff like that. Now, the moon doesn't have an atmosphere, and we see practically no lensing, as we shouldn't. But this is what we're talking about here in this kind of level. Now, if that is incorrect, like the idea that that's wrong and that space-time does not bend, we are basically back to asking what causes gravity. And the second part of your question, unfortunately, I had already forgotten it.
That's all right. That's all right.
Do you know what it was?
Well, can we first establish that at best we disagree on the lensing effect?
Well, of course, you're going to disagree with everything that I say.
No, not necessarily. No,
No. It's okay. You will. It's normal to.
Could we also agree that you have not satisfactorily explained to me how the electric universe theory replaces gravity in the lensing effect?
Yeah, that's the next question then, because that was what I was saying. Like, what part does this play and how?
I just want to know if you would agree with me that you have not satisfactorily explained to me how the electric universe theory replaces gravity in the instance of the lensing effect. Would you agree with that statement, sir?
Well, I couldn't, unless I was really convincing, I wouldn't expect that I could possibly do it with just a lensing effect. But it was the first, but I totally agree that no, I'm not Dr. Ed Dowdye, and I don't have any of his wonderful data to show you.
Okay.
However, I could give you the reference and let you see it.
And that's fine. And I would be happy
and it's totally fine. Yeah.
I just want to establish that you hadn't satisfactorily showed me how the electric universe theory would replace mechanically the lensing effect. And
no, right now that's just there's several problems with astrophysics alone on that front.
Because I concede that gravity, we don't know what it is, right? There's theories. There's quantum loop theory for gravity. There's chameleon theory for gravity. There's the graviton theory for gravity. There's the Higgs boson quantum field theory for gravity. There's the relativistic view of what gravity is. We certainly don't know what gravity is. Okay, and I'm not saying I know what it is. I'm only asking you to replace every piece of the mechanics that we have filled in with physics with the electric universe pieces, so that I can see a clear delineation between those two and how it works, right?
That would be perfect. Then let me just explain that one real easy. So in the electric universe, the idea that instead of using the bending of space and time, idea of why this is happening, there is an alignment of the internal structure of the nucleus of the bodies of the atoms, and they are aligned that way in a dipole fashion. It's not done because of anything but basic charges. And
now you might have to be a bit more clear about that, what you're saying, because can we just go back over what you said there? You said that there is an alignment of the core of atoms?
Nucleus, yes.
Nucleus. And by nucleus, you mean?
Oh, well, I guess I mean protons and neutrons in the conventional theory. There is an alternate one, but that's a little bit later.
And those neutrons and protons are made of what?
Well, that's a very interesting question.
Do you know?
We don't really know.
I'm just curious. I'm just because
I've heard the quark theory. There's an argument that there is a torus in there. I've seen lots.
They're made of quantum particles called gluons. Gluons are the force-carrying particle for the strong force, which is the force that keeps the nuclear atoms together, that keeps the protons and the neutrons, which are the nucleus of the atoms. What keeps them together is a force-carrying boson particle called a gluon, and it's responsible for what's called the strong force, right? So when you're saying that the nucleus of an atom is aligned in a dipolar fashion, that's impossible. Like, the only thing that lines up concerning atoms in a dipolar fashion is atoms themselves, not the nucleuses of atoms, but atoms themselves, because they line up in dipolar fashion in that way when psychotropic substances are taken in the cytoskeletal structure of the cell of a neuron in the brain, which is a part of the OR theory.
You're talking about?
I'm talking about quantum consciousness, and I'm talking about quantum theory.
I don't really. I think that they're probably really messed up on that one.
When you say you think that they're really messed up on that, are you saying that all of the scientists that propute quantum mechanics are really messed up?
Or is it a specific instance
I generally agree with Einstein in that sense that by doing statistical analysis and coming up with the clouds and so forth, I think that they've done some great work on trying to figure out, but this is, again, one of the reasons why we're coming to an end of the predictability of the
What did you mean when you said that
method.
the nucleuses of atoms were lined up in dipolar fashion? Where were you going with that?
They're slightly offset because of their generally overall positive nature, and they'll be pulled towards generally negative planetary source, for example.
Wait. Could you slow down and say that again? Where were you headed when you said that the inside of that the nucleus of an atom was lined up in dipolar fashion? What was you saying about that?
Well, basically, if you could picture, for lack of a better model, we'll just pretend the Bohr model in our heads, and we'll just do the circle and the nucleus with a little tiny dot in the middle.
Bohr.
Yeah, well, I'm just giving you simplifying it.
No, I understand who Niels Bohr is. He's one of our greatest scientists, and I know what he's famous for, and I know what you're saying. You're talking about that model. Are you asking me to put aside that knowledge and accept an alternative knowledge?
No, I'm simply asking you that telling you that there was a gentleman who, I think his name was Setterfield, who came up, Barry Setterfield, I think,
okay.
But he came up with the idea that basically there's an offset towards this nucleus, and this is the reason why we see some of the effects that we do.
An offset to the nucleus? What do you mean by an offset?
Well, instead of the nucleus being exactly in the center, it's slightly pulled to one side.
Okay.
And this slightly pulled to one side is because it's generally positive, and it's going to be attracted to the negative surface.
So pulled to one side of what?
The atom itself.
The nucleus of the atom is pulled to one side of itself, is what you're saying?
He said,
if you pictured that the atom was a circle with that is the electron, and the dot in the middle would be the proton, then it's slightly off to one side.
So no.
More of like the dot in the middle would be the nucleus, not the proton. The nucleus is comprised of the.
I was thinking of it just a hydrogen model for the basics of it, but yeah.
Right. So the hydrogen model would look like. What?
You'd be like more egg-shaped, Neil? Is that kind of what you're getting at? Instead of spherical, it would appear more
be slightly to one side.
Okay.
Yeah,
like egg-shaped. Okay, I get that. Okay. I didn't know if you meant that the nucleus would be offset from the orbits of the electrons, or if you were saying that it would be somehow misshapen in some way. I wasn't sure.
It would be a distortion. I think this distortion probably also explains this mass increase that we seem to see when these things are shot down. They're gaining a lot of energy as you put so much electrical magnetic energy into them, and of course they're basically essentially distorted. And the distortion, of course, we come across as mass. And this is
do you
what
have
is
any
causing,
pictures of the distorted nucleuses of an atom?
Well, you said there was an author or somebody, or not an author, a physicist or something at one point in time that put.
And also, I'm wondering how does spin work? Like, how does spin work if the nucleus of an atom is egg-shaped? How would spin work?
Or is that what gives atoms
we
vibration?
already know that these things are generally in a field, and I hate to use the word quantum field; it's just so overused.
What you're talking about the electrons?
Yeah.
Okay.
That's what we're talking about, right?
Yeah. That's why I'm asking how spin would work if the nucleus was odd shaped.
Well, I assume that this distortion requires energy to overcome. So of course. This could have a lot to do, but I'm not actually an expert on that level down there. So let's just be be honest. There's a
yeah, that's fine. That's cool.
I'm much more. For example, I'm much more inclined because of just my nature of electromagnetism as my base to go with models that seem to work on that general idea. And one of them is that, for example, there's
what
no real
idea?
neutrons. There's actually an actual electron and another proton put together there, and that's why they break up when they come apart, and that's why they break up into an electron and a proton, two base particles.
What does
he's saying? So let me see if I understand it, Neil. So you're saying that when these things take on speed, the mass that they take on, the reason that they throw off particles as they continue to take on mass is because of this off-centered shape, and it causes them to like vibrate.
Well, I think that I was actually going on a different direction there.
Okay,
but I
I'm sorry.
To totally true that the distortion, I think, has to do with the charge of the body. That charge has to do with basically what comes across to us as mass, and there seems to be an inverse proportion to charge and mass of the body itself. And we seem to already know this to be the case because the sun is made of hydrogen, apparently, and the gas giants are made of gas, apparently. Saturn can float in water, apparently.
I know you don't want to go into the quantum realm too much, but I was just curious when you were talking about the gaining of mass in the atom.
Well, actually, I was making a cyclotron, but yeah, sure.
Well, what do you mean?
Whenever you're sitting around that the CERN there, and of course,
I'm not sure how cyclotrons just got involved in this question.
He was proposing that there's a connection between the way that they discharge particles as you speed them up, they start tossing off particles, right? And he's proposing that there's a connection between that and CERN, and
but that's not how a cyclotron works, though.
No, actually, that's not. I simply shouldn't have used that word.
Oh, I'm sorry.
That's all right. Okay, I'm just making sure, man. I'm just making sure I'm following your logic here.
No,
I'm trying.
It just came out because I was spinning my arm at the time and I was saying cycle. No, just say CERN. Okay, CERN.
Yep. I had to write CERN and talk to their public advisor to get detailed, high-resolution pictures of the Large Hadron Collider.
That's what it's called. Thank you.
Oh yeah, no problem.
The gentleman. There's actually a gentleman who was at Bath who's up for head of CERN, and he's like a little bit. I don't want to say a little bit EU, but he sees merit in it because of the points of view that he has to deal with, and the answers become a little bit clearer under that point of view. So,
but at least between us, would it be safe to assume that we would have to differ on some of the issues that we're talking about with atoms?
Of course, we're always going to differ until you are there, or I'm completely convinced that I'm wrong.
Okay.
And that's totally possible.
And would we also be able?
I don't think so, but
would we also be able to agree that you have not satisfactorily explained how the electric universe theory replaces the mechanics that quantum mechanics has in concerns of gravity, such as the force-carrying particle known as the Higgs boson and how it relates to atoms?
I don't even know if that thing exists.
Well, it was proven to exist by CERN laboratories with the Large Hadron Collider.
You can't prove something in the positive, remember. You can only not disprove it yet.
No, they
things are falsified. That's how science works. This is one of the biggest issues that we have
data?
with regards to.
Did you just say that CERN falsified data?
No, falsification is the essence of science.
Oh, I see. Okay, but
no,
like for real,
they actually they're doing good work.
They certainly released a lot of public statements that they discovered the Higgs boson. If they didn't discover it,
well, he's saying he doesn't know he don't believe that what they've discovered is the Higgs boson. Then is that what you're getting at, Neil?
Well, the thing is that we don't even this argument that whether or not they've even have an idea. I mean, they keep on going for more and more particles. It seems to be a failure of the paradigm of trying to break things into smaller and smaller pieces, as opposed to something that we might have missed on our way down here. This is why we're getting into speculative science, where things are 80% sure, 90% sure. That means we're playing ball or we're playing cards. We should know exactly every single step.
But that's why they're building machines like CERN, for the empirical evidence needed for some of the theoretical physics of quantum physics. I mean, after all, the Higgs boson was a theoretical particle until it was proven to exist by CERN laboratories. So they're actually empirically testing some of the things.
Well, they've also said that they found gravity waves, which is probably not going to be the case either.
Okay.
Which we've already seen problems of that. And for obvious reasons. I mean, gravity, of course, being an instant force.
Well, let's move on to a third topic then. And since you brought up gravity waves, can you explain to me how gravity waves, how the electric universe theory explains gravity waves, right?
Yeah.
And in particular, the formation of stars and the spiral rings of spiral galaxies. Could you address that?
The spiral rings of spiral galaxies.
Yeah, the spiral arms of spiral galaxies.
Like,
star formation.
Are you asking? Does electric universe theory have a way of explaining these
star formations that occur in the spiral arms of spiral galaxies?
Or how does it explain that? Okay.
How does it replace normal standard given physics,
standard model physics
that includes gravity? Yeah. Like, how does that?
Gravity is in the electric universe model. Gravity would be the leftover of the ashes of a prior electrical events. Because what made these spheres all around us is not, in the electric universe model, not a slow accumulation of mass over time or something weird like that.
You're talking about planets and stuff, right?
We're talking about things that have gone through what we would refer to as a pinch. Pinches make spheres. It's all that dust that you get
when you say spheres around us, are you talking about planets or stars or both?
Both.
Okay. Just so the planets and the stars.
In my model, see, I'm talking crazy already. No. In the general idea of the electric universe, there's debate on what the sun is or what stars are. But if we're going with simply the Donald Scott book, The Electric Sky, which is generally considered one of the Bibles of the electric universe, would be that fissioning of stellar masses occurs when they can no longer accept any more charge on their surfaces. And the reason that they have charge on their surfaces at all is because they are in electrical circuits. And the reason that how they are in electrical circuits, the heliopause would be like the electron shell, for example. And it is up against other shells around it. And currents are allowed to flow through these, which of course are connected to the spiral arms and so forth. The spiral arms themselves and the center of the galaxy is actually where two currents that have been feeding onto this thing have pinched together and twisted. And the reason they have done this is because of the right-hand rule, and it basically is a Faraday motor. There's nothing strange about that. Same reason that the sun has a torus, that the Earth has a Van Allen belts. It is a simple Faraday effect. We are a north-south arrangement. It is a spinning top. Voila, you have a Faraday motor, which you can build with a magnet, a battery, and a piece of wire, as you know. So it is a very simple machine. And of course, it's a horribly working one because it's spheres. It's like being disks, really, because it travels a lot better. And we get these secondary currents generated around it, which, of course, we see in the sun and we can see on Earth as these bands. And, of course, Jupiter has the same bands. And the reason that they travel in opposite directions, of course, right-hand rule, and, of course, they're going against each other. So this is just why we see the separation at the equator, for example, on Earth. The atmosphere in the north generally does not mix with the atmosphere in the south, and so on. So,
well, no need to extrapolate any further on that.
Well, now the next question is then, Eric. Then what does the standard model say, and how do those?
Well,
differ?
before I go there, could I explore this a little bit?
Yeah,
more?
yeah.
Okay, could you differentiate for me the process between the pinch off that creates stars and the pinch off that creates planets and the pinch off that creates things like brown dwarfs and gas giants?
Well, actually, we'd be better to talk about the Hertzsprung-Russell diagram for the HR diagram for stars.
Okay.
Donald Scott proposed that the easiest thing to do is that the temperature of the star that we consider like to be, bluish white to, the dwarfs and stuff, that is actually something that we see in plasma if we change the words to it's not age that's causing this or something that they're burning out of fuel. It is how much current amps, basically current, per square meter on their surface that they have to deal with. If they're at a certain point, they have hit maximum load and they are white, bluish white all over, and they are as much current as they can handle. If they get any more current, they will have to fission. And by fissioning, that means that eventually a part of the positive core will touch the outer wall of the outside, and all of the electrons on the surface will rush to that point and barf out another sphere. And this sphere will be pinched because of the effect. We also see half-pinched bodies. For example, the moon Pan. Is Celeus or Oedipus, whichever one of that is, has the ridge around the middle. It wasn't quite pinched off properly. And this is and these are effects.
And now, how is it that the planets get formed?
Well, it depends on which ones. Each one gets burst in a different event. A lot of these moons probably came from the same event, for example. But there are also Jupiter probably came from the sun, for example.
Well, I guess what I'm saying is I follow what you're saying about why there would be different brilliances of stars and different temperatures and
they're just basically a body.
Sure, right. And I can even get behind that. Those are all really good explanations, and they're great alternative explanations for stars, right? Because you could achieve those things in that way, but you'd also have to assume that there's this ether of power out there that we can't see, but there's a huge amount of power in it, and it's just powering all this stuff away. And that's fine too, right? Because
actually, I don't think that's not the case, but I understand what you mean.
Well, then I would ask you where the energy comes from that's powering these stars.
Well, they're basically asking me what causes the universe, and
no, I'm only asking you what powers the stars. That's where this all
originate from. At the end of the day.
But is it measurable? Because this is something.
Oh God, yes. We can see the fields that are generated by the electric currents all the time. The way that it's explained away by astronomers is simply making the E field equal to the B field, and they simply say that it is superconductive. But that's not true, because obviously we know in laboratory plasma, although a fantastic conductor, which is what the solar wind is just plasma, and so the same with our magnetic tail and all the.
So how are the stars powered?
Pardon?
So how are the stars powered?
Well, they're basically powered by the electrons that are the amazing amount of electrons per square meter of this particular thing that are coming down the magnetic field lines of the actual star towards the center and getting shot out along the ecliptic, just like the galaxy is.
So you're saying that the magnetic field of the star powers the star?
Well, no. In fact, the iron content, as it gets broken down and fissioned down.
In electric universe theory, what powers the star?
That's external currents.
Okay, where does those external currents come from, and how much energy does that external current have to burn into the stars in the universe?
Oh my God! We are talking about let's just say 3 electrons per square meter, and you're dealing with multi-terawatts of power.
So then, as I just said earlier, there is this other plane of energy that has a massive amount of energy to power every star in the universe that we can't detect. And I didn't think that was absurd.
I don't think that's the case.
Okay,
I think we
so
detect
then
it
we
very
have
well.
to back up and say, because you kind of just led us to a point where you were just saying that there were terawatts in this energy field that created the stars, right?
Well, you got to think about just the sheer volume that we're dealing with here. But we're talking about this. We're talking about this the sun, which has, as we know, has these planets along it. But they're mostly staying at a certain disk. If they go up too high, they're generating more of an electric load. They must go down closer towards the ecliptic. That's where they want to be. Things don't like being. This is why comets, for example, are never following the exact same course, but seem to come at the same time, but they follow a daisy wheel around the solar system. This is just basically the right-hand rule. As they get close to the charge point, they suddenly have a higher turn radius, and they travel out in a different trajectory as they would just a simple orbit. And this is because they're highly charged bodies closing in on a highly charged body. But anyway, the sun itself, of course, it is connected to what we call the local chimney. And this local chimney is a pair of currents that are traveling through this. We know which direction these currents are traveling. We know that behind us, for example, Sirius, or ahead of us, depending on which way, but technically Sirius, therefore it would be down below. Sirius stays at the same angle to us, so it's staying behind us on this current. And this current is basically powering all the stars around. And we're talking about square astronomical units of sheer current traveling diffusely, it seems, but it pinches down and it gets closer to magnetic fields, as you would expect. And it has to follow the gradient. That's just electricity 101. And we know that these bodies have an electrical charge potential, as we know that the Earth has one. We can measure it. The sun, obviously harder to measure, but have come up to somewhere along the vicinity of so many billion volts. And we're talking, and you can also see how much power it has by its shooting, because we know that there's more powerful stars out there because we see the effects of cosmic rays that can penetrate right through our shield. Right. So we know that there are stars out there on magnitudes more powerful than this sun beside us, because of what we get hit with.
So energy's never lost nor gained; it only changes states, right? So
that is generally a rule, yeah.
Okay, so
I don't see any other one right now.
So if we think about it in those terms, is it the planetary bodies and these bodies of masses and gas masses and stuff is in the theory that their movement around each other and through this space causes these sort of like running a magnet past a coil induces a current? Is it saying that just their movement through the cosmos near each other causes this energy transfer?
I do not know what powers this. Is clearly power. There is a direction. We can see that we are traveling. Our local group of galaxies, for example, are on itself is a pinch on a current which is traveling towards the great attractor, and we're traveling on, and these are pinches that our galaxies are on, and we can see these chains. It is like a it's not an explosion per se. It might be an electrical explosion, but we are seeing some discharges happening between 2 points in the universe somewhere, and we are in the middle of that.
Okay.
And the reason that the stars and everything happen is because as these currents come in, the Lorentz force and Markland convection pulls everything together and sorts it, and barfs out a bunch of spheres. Some of these spheres are large enough to actually glow because they have so much current pinging on their surface, and they're not that big. Even the largest star is simply a tiny little tiny thing. So these things, their atmospheres or their heliopauses are up against each other and form a cellular network, which would be generally what these arms are traveling on. But there's another stage in between where we can see that there are loop currents going around these arms, which we are part of that loop current. Our local interstellar chimney is attached to one of those, it seems, because we're trying to figure out, because we can see it and we know historically what it did. And we know about the Pleiades and all that stuff from way back when. So we know there's something to it. But it has to be connected to the arm of the galaxy, because we're at that point that we're seeing clusters of stars.
Okay.
So this is where we're at, basically, seeing where these things are connected. And we know that the nebula themselves we know that they're like, we thought they were clouds, but when we get the new pictures are showing us that they are just sheer unbridled amounts of filaments. They're little filaments all over the place. And that is a sure sign that you're dealing with electricity.
That looks like lace or something in the sky kind of thing, right? Yeah.
Oh, yeah, just like the aurora.
Well, it definitely has that. It definitely has that same sort of appearance of things like a plasma ball and that kind of stuff. I've seen that, and they're beautiful. You're right. They're amazing. All right,
we see stars or galaxies on these that would be. I mean, we make them in the laboratory in plasma. Okay. But they only last to imagine a galaxy as a transitory event is kind of hard.
To be honest with both you guys, I've never contemplated this at this level. Okay, so now So I don't know what the standard model or this whatever you guys it's called the standard model sort of idea of how this stuff comes together is, right?
Yeah.
So how does that line up, Eric, then with what Neil's talking about? So what is the standard theory, and then how does that kind of line up with what Neil's talking about?
I think I can do that succinctly and answer some questions that Neil wasn't able to address, at least. So a star is born, right? The star is born because there's a
great movie. Yeah.
There's a dust and all out through the universe, right? And gravity waves plays the part of acting as a ripple, and these clouds of dust and gas that he says are filaments, right?
Yeah.
When a gravity wave hits that, and a ripple in the space-time continuum hits that, it causes those molecular parts of that dust and gas to get closer to each other, as opposed to being all spread out like the second law of thermodynamics would dictate, right?
Okay.
And then once that happens, gravity takes over again from there, and it starts drawing these things closer and closer to each other, right? And it packs itself in until the pressure of the gravity causes fusion to occur, because things are fused together by the pressure and force of the gravity, and a star ignites and begins to shed light.
So gravity waves don't play a part in this stuff, though once...
Well,
right.
It's gravity's played a part twice now in the birth of a star, right?
Yeah, right. According to the standard model,
right? According to the standard model. Also,
but that also sounds an awful lot like when you talk about these. Where do these gravity waves come from?
They come from the core of the galaxy. They come from neutron stars. They come from singularities. They come from all sorts of sources.
So they're not like. So they're saying gravity waves don't come. They come from all different directions, kind of.
Yeah,
idea.
But they can emanate from the center of a galaxy or an astrological object like a singularity more strongly or more directionally, right? But they do come from all directions of the galaxy too, because it's a ripple, right? So it doesn't dissipate in energy.
Now, how do they? If they can't measure Eddington on that one, because he was actually Eddington. Because he chastised Chandrasekhar for his idea of a black hole,
and that's fine. But let me just. I thought it was good. Let me just finish with.
Of course.
With that. So these first generation stars are basically fusion plants. They start packing stuff together, and they start making elements that didn't exist before, such as carbon. So when the life cycle of that star ends, all that gas and that fuel gets burned up.
Right.
That's burning, that started from the pressure in the first place, the fusion, it blows up, and it blows out all that shit that it made, which is what we call a nebula. And it's a bunch of gas and elements and things like that, not electric filaments or anything of that nature.
That's why they say like heavy elements and stuff are made in stars.
Exactly.
Right? Okay.
Right. And why you're made of star stuff, because you're made of carbon, right? Because what happens is gravity takes over again in this scenario. A third time, or fourth time, really, if you consider that the gravitational influence is what forged these elements to begin with and causes the star to basically explode out as it ricochets off of its own collapsation.
Yeah.
And when it does this, it seeds the nearby area with the gravitational waves and the dust and the gas to start accretion along orbital lines, and the accretion takes the form of a sphere because it's the most energy productive geometrical shape, and spheres create angular momentum, which is why everything we see is round and spins pretty much in space, and just like the star itself. And the planets accrete around the sun, and
then moons accrete around planets.
Exactly.
Idea,
some
right?
of them do, some of them arrive in different ways, like our moon.
Yeah.
But, so that's basically why I was asking, because there needs to be a way that the electric universe theory provides for the examples of this. And I accept the stars. Go ahead.
Doesn't that sound okay? So here, I'm ignorance here. Okay, both you guys, right? You're both talking about something though that sort of then, in an essence, powers creation that comes in from these cosmic sources somehow, right? So now, to be fair though, have we measured gravity waves yet successfully, or are we sure that that's what we're measuring yet? I know there was some debate about that, right?
I have debate on just simply because of the formula itself has no wave to it. It's an instant force gravity. So it's being projected out into the but it's being projected out into the universe. No, I mean, if gravity changed instantly on this planet, then just because it follows the same as Coulomb's law. It's force equals, then there's either big G, or in the case of Coulomb's law, K, and then it is just mass 1 and mass 2, bracket, close bracket, over R squared. But the same formula is used for Coulomb's law, and we don't take time into effect. If charge changed here, everything in the universe feels it instantly. And that's how that works.
That's kind of the concept that everything in the universe is technically connected electrically somehow throughout.
Well, it would have to, if Coulomb's law is true, yes.
Okay.
And it seems to be. But we're not talking about waves, though. We're not talking about transversal like light or anything. Like this would just be, and it would just be if, like, for example, charge change here, then, or grip mass changed here suddenly, then everything else would feel it instantly. Now, we don't have any ability to do that over any large distances, really.
Not at the cosmic scale.
Whereas normally what they say when they give out, when they get interviewed by reporters and stuff, the scientists that work on detecting these gravitational waves, they'll say it take millions, billions of years for these gravity waves to have reached them.
Yeah, because they have a light speed limitation. Yeah.
Yeah. As opposed to instantaneously, which is what he's saying. I'm just pointing out.
There's a speed of light. Okay, so you're saying then there's a connection that supersedes the connection of the speed of light. That sounds quantum to me.
Well, that's just I don't like that word because it feels like a buzzword in many cases. But to be fair, it just in the formula, it just means that there's no time in the formula. If you look at the formulas for either of these equations, there's no time involved.
But you did concede, Neil, that we really can't test this on any cosmic scale. So you don't know. There may actually be limitations in that where it wouldn't be felt instantly, right? Necessarily because of that, because that doesn't have, you can't put that in the equation, because how do you measure it on the surface of the Earth kind of situation? You can't measure it cosmically, yeah.
Well, and of course, we had no right to, and I think this is not. This is something that was rightfully critiqued, I guess. I'm not sure who his name was. He had a tiff with Newton, but people were calling it the universal law of gravitation, and I think that was probably the first issue that we had, because by calling it universal, we've taken it off of Earth without measuring it, and we've noticed some problems with it already. Like there's issues with sometimes when planets, or sometimes when our space probes get close to a particular layer, it seems that they have a change in potential mass, and they don't know how that happens. The Pioneer anomaly, for example, is another one of those where it's off course, but of course they think they've explained it by latent heating or something. So I won't try to complain about that. But there's also a problem with the way Mercury orbits. So there's several little issues here that are these little anomalies that could be accurately explained. I now know what the other part of your question was at the very beginning. It was about time dilation.
I was gonna ask about that. Yeah, because I just wanted to reiterate that that's one of the staple experiments that you can do, that almost anybody can do in their home. You can build a cloud chamber. Do you know what a cloud chamber is, sir?
Back on the cloud chamber.
Is.
Do what?
They're awesome.
Yeah,
in fact, I find them to be one of the best things. You know, you put a piece of uranium in it, and you can see the effects of the charged particle or the particles flying off of it, which is amazing. So
that's
because it's a real effect. You know what I mean?
Yeah, I do. But I am a bit confused about maybe our definition of what a cloud chamber is, though.
You're talking about the thing that looks at the cosmic rays that are coming in from. That's what I thought, and I'd never heard of one until you explained it.
The ones I've seen are the ones that you actually put a piece of uranium in it, and you watch the effect. The particles shoot out of the uranium in all directions.
I got you. Okay. Yeah.
That's all. Same thing, though.
Yeah. What I'm talking about is just a vacuum chamber filled with alcohol. Vaporized alcohol, and with a magnet underneath of it. Definitely not uranium, just a magnet. That's the most expensive part of it. And basically,
the magnet would attract the particles.
It would, and the ones with mass. Because so at any rate,
charge mass. What?
At any rate, charge. That's good. I like that.
This is the issue. I think that a lot of this stuff is being misattributed because some things are very close.
Okay,
I'm not saying that the sun is orbiting the Earth because of gravity.
You're not.
Or sorry, the other way around.
But we don't know what magnetism is either.
Because of electricity.
Scientifically speaking, we have no idea what magnetism is either. While we're on the subject of talking about things that nobody really knows, right? We're all bordering on mysticism to some degree, right?
You're absolutely right.
Specifically, though, what I'm talking about is time dilation, right? The cloud chamber is because it comes at the end of this, right? But the idea is that there's subatomic particles and that's coming in from orbit down to our planet, and their half-lives are not long enough for them to come all the way down to our planet. Like they would dissipate into another particle, right? They would join with other subatomic particles and create a different particle. They have a decay, and they would decay into this other particle, and that's what the half-life is, right? And that's going to happen before they reach the Earth. But because they're traveling close to the speed of light, they have a time dilation that allows them to actually reach down to the Earth so that we can capture them in cloud chambers. And the ones that actually have mass, if you have a magnet underneath the cloud chamber, you can see them arc. And depending on their arc, you know what particle they are because it lines up.
Wouldn't it be if they have charge? Because it can't be if they have mass.
No, it could be. No, I absolutely agree. It could be charge.
I mean, just because that's what travels down the quote-unquote magnetic field lines. Wouldn't
it by definition be charge if it was a magnet that was causing it to alter its path?
Well, he means charge as opposed to mass, I think.
Well, I didn't know. I just meant that it would follow the magnetic line of force.
Well, if it had mass, it would, but not necessarily if it had charge. I mean, after all mass has a charge because there's matter and there's antimatter, right? So I mean, everything has a charge. The electrons have a charge, right? And there is such a thing as.
It would be an ionized particle. Would have to be.
But what's ionized is the alcohol vapor. That when the particle travels through it, it ionizes the alcohol vapor, which is what makes the streak.
But still. Magnets don't affect non-ferrous things. Okay, they just don't.
Yeah, that's why I say. So it could be considered the charge of the particle.
But that's what I'm getting at. Then,
but it comes with mass.
Isn't that an attribution to the fact that there's an electrical effect?
I would say yes. That's why I said. I mean, that's why I said nobody knows what a magnet is either.
Right.
Because it could very well work under. I can see it
am I
that it
missing,
would work.
Am I missing?
No.
You telling me you're finding a very strong argument?
I'm just saying for the electric universe there. Yeah. I mean, I could see with the science that I know that that would be a good strategic move in the chess game. Like, hey, man, talk about this because it's
here's
relevant.
A visible effect you can see.
Well, and it's also an area that nobody can definitively tell you what a magnet does and how it works, right? Nobody fully understands Maxwell's equations and the implications. Nobody fully understands what gravity is. Here is a crux where these two things come together.
We think that we could actually fix because up to a certain point, Einstein wasn't wrong, and some of the issues that come from like some of his, like for example, what he won the Nobel Prize for was totally worth it. We use that all the time for photovoltaics. So I love that kind of work. But when we have the issue of like, for example, the time dilation thing comes right back to this. The reason that the half-life is questioned becomes, well, here's the perfect example. We don't know, well, we're starting to know now, and this is one of the things that was a big focus of the Bath conference, actually, unbeknownst to me. It just sort of happened that a lot of the researchers are all following into the same thing because they're starting to notice this. But basically, a gentleman took so much material that was radioactive and completely turned it into neutral material because he accelerated the half-life by putting it into a highly ionized field. And so by changing the electrical environment and the electrical pressures around material, it will change their half-life. So the question becomes, when you send this plane with the atomic clock into high orbit and then travel around the Earth on the Concorde, and you come back down and you notice the times are different, and you look at that and say proof of time dilation, well, the electron pressure at the surface of the planet is completely different than the ones at 50,000 feet.
I would agree with that, with one stipulation. It's not just a matter of the distance between them and the Earth. It's also a matter of how fast they're traveling. So, well,
and then of course this again, how does the field of the craft change? Because we already know that when you go to, for example, you're on a aircraft carrier, you cannot just touch the plane. You have to ground the plane out first before you touch it, including the canopy.
That's a when you're fueling it thing, but that's you have to ground.
I'm just saying
it's just static electricity is a bitch.
Yeah. So, but I'm not talking about
helicopters are the worst.
Well, no, but if you're talking about the Concorde traveling at Mach 3 above the, you are talking about that.
But I'm not talking about talking about a whole different. I'm not trying to distract from the subject here by talking about an airplane and needing to be discharged, right? That's not what I'm saying, dude. What I'm saying is that those calculations, look, atomic clocks have cesium-101 atoms in them and they vibrate, right? And that's what an atomic clock is, right? And the calculations aren't just how far away they are from the gravity well of the Earth, which is a part of that because gravity does slow down time, but it's also how fast the satellites move. They have to compensate for that too. If they don't,
you're talking about the GPS problem.
I'm talking about any atomic clock, any cesium-101 atom that's moving at this particular speed away from the Earth at that particular distance. You have to math it out, and you have to adjust for both of those. And I'm saying that because you have to do that, that's what proves Einstein's time dilation. That's like another thing that proves it.
There's a big common misconception about that, because they are seeing problems you just defined.
Did you just say it was a big common misconception? That there's a big. Did you just say there was a big common misconception about Einstein's time dilation and the vibration of cesium atoms? Did you say there's a big common
with regards to especially the GPS satellites?
Okay.
Because the calculations are not happening. They have to correct for them, but I learned what they do to correct. It's not actually fixing the problem; it's just going around it. And one of the issues that
that's the point, right? They're using math to go around the fact that these things are doing something different. They have to use math to compensate for it, go around it.
As perfect as sacrosanct as Einstein predicted. They are considered to be
Are you saying
proof of Einstein.
they drift, so they have to be
Yes,
constantly adjusted
they're
for
not
drift?
always accurate, and I can show you some papers on that. But it's commonly
What's
hidden.
not always accurate?
The GPS, basically
The
the
clock.
proof. The clocks are not doing what they're supposed to do, and they're not doing it according to Einstein perfectly either. Although they are being affected, but at certain varying degrees.
Yeah,
This
but
is
they
the
are
same
enough
issue.
that we can use GPS and get around the planet.
No, he's
easily.
not. But he's
Of
not
course.
arguing that. That's not what he's. See,
No, not remotely arguing that.
So
no.
in
fact, I use it.
I love him. What he's saying is that these things have a predictable clock, and because of their geostationary orbits and all these kind of things, they're supposed to do X. Okay, and they're not. And periodically they have to go in, because this is what, in an instrumentation standpoint, we call drift. And all instruments drift. I mean, it's like that's why we put them on these things.
But they're
called
drifting
calibration
because of the
schedules.
natural forces of Einstein's.
But he's not arguing that. He's saying, but what I'm hearing you say, Neil, is that the way they mathed it out is that they didn't go enough decimal points. Or
that might be an accurate thing to say, or they could be using
I
the
didn't
incorrect
say
theory. And what I mean by that is this is not arguing the data. See, this is the same issue that we have when we go into the quantum realm, where we start getting into the percentages, like 80% chance and stuff like that. We're starting to play dice, and we should be able to be absolutely exact if we totally understood what we're talking about.
We probably could be. It's just not necessary.
Well,
right in college, we're already using it to get around and using it for things that we need. Right?
Yeah, it's got an accuracy about 3 meters.
Yeah, there used to be a built-in inaccuracy, in fact, until recently. And
that was a terrorism.
It was,
thing,
I know, but my point is they had to build in an inaccuracy because it was too accurate, and now it's pretty doggone accurate, right?
So regular GPS. Yeah.
So I mean, they probably could be more precise with the math.
There's a next generation that's coming. It's lower orbit, but that's not.
That's having to do with the location of these particular satellites in dealing with the fact that they can calculate where they are in relationship to other things on the surface.
Yeah.
So they actually have correction that they can use to make sure. And I'm not saying that these people are not doing their best, and I'm not saying that the people are not doing good science. In fact, I'm just thinking that if we're at this point where we're questioning the foundations of some of these things that they're built on, this is a good thing to do.
But who's questioning it? Who's questioning this?
He's saying the electric universe community is sort of positive.
Well, actually, he phrased it as a common misconception. He didn't phrase it as a group of people.
Oh, okay.
Like the way I understood it was.
The common misconception is that there is that thing is 100% like, we know how to fix it because we know this, and it's not exactly true. It is giving us the ability to have to not have to fix it as much, I guess, which is great.
Well, we only know the universe through the best instruments we have available to us right now, right? So, but I mean, so the things like drift and stuff like that can also be attributed to that, nonetheless, right?
Yeah.
Oh, yeah, and this is some of the things that we know because we're basing this stuff, like I said, off the clocks. But if these clocks are in a different electrical environment, especially now that they're in space and they are past 500,000 volts away from us, and they're still within the electrical sphere of the Earth and the Moon, basically, because they're inside the magnetosphere. But once we leave that, then we're now in the domain of the sun. The sun's solar plasma pinches down the planet's magnetospheres and their plasmaspheres, which should be just called plasmaspheres, I guess. And of course, the Earth has a fairly big one because we have a fairly big magnetic field. But Venus, for example, is just it has only a three planetary diameter magnetosphere or plasmasphere, electrosphere, I guess, because it's based off mostly its capacitance. And this is, of course, has a long streaky tail. So if we could see it, it would look like a line almost across the heavens.
Okay.
And then that tail comes by us every 8 years or so. And then our tail goes and brushes up against Mars. This is when they get their dust storms, of course, because that's why every time they go, it's going to be perfect, guys. We're going to get right there. We're going to be the closest approach we've ever been. Let's look. Oh, it's a dust storm. Damn. I wonder why that happened. Because our tail is tickling it, and our tail will tickle Mars. And if it's doing that, it's exchanging charge. And now suddenly you have 6-7 mile tall friggin' dust devils running across the planet. Because it's just totally ionized dust. And that's what cleans off that Curiosity rover all the time. Like they go, why is these cleaning events happening? And goes, we use cleaning events all the time to clean actual PV panels in real life right now. We just turn on the backwards voltage.
Well, that's it.
Watch the dust fly off it.
In industrial dust collectors, that's how they do it too. They can reverse the.
We shouldn't be surprised it happens. That's all I'm saying. We should also not be surprised when things crash into it because because you're landing on another charged body. I mean, it's not that bad if you're traveling from the Earth to the Sun. The biggest danger, or the Earth to the Moon, but the biggest danger, not just the Van Allen belts, is the same thing that if you're starting to go closer and closer to the Earth, you're picking up charge like a MFR. And I'm telling you, that's what that causes, that coma. It's not friction or anything. You're bleeding off charge. Because this is an electrical coma that happens around every time you start putting your Langmuir probe into it. And the tail of the spacecraft has a plasma tail reaching up into the heavens. So now you're like a wire reaching towards an anode. You're asking to get zapped.
Right.
You know, I'm amazed we don't have more of these things blow up. You know, like it's crazy. I mean, electrically speaking, and we should have known this because the first thing we sent into space there, we started taking pictures, and all the pictures had big lightning streaks across it because we didn't have it insulated.
Right.
They didn't think it would do that. It did that.
Yeah,
the tether experiment didn't work. Same thing because, I mean, they took it. They were trying to run it across a magnetic field. They didn't take into account the electric field. You know, it's just little things like that bother me as an electrical engineer because you should be able to calculate this. I can calculate that the Earth has about, this many farads and this many, and it just, why are you not paying attention to this? You're NASA,
Now, I found this really, by the way, guys, both of you, I found this fucking amazing. I'm so glad we did this. But I really want to circle back to, there's a place in here, though, that you guys both seem to find some common ground. And I hate to go back to this, but it goes back to this cloud chamber thing in the way that. So, Eric, you're submitting then that there's a visible, measurable effect that magnetism has on particles, and that aren't necessarily ferrous, and that. So, how do we build? Is there a way then to quantify this and build out from that? Because it's already been done, I think. But
he
has. He's saying that. That's what he came up with.
I think that this would be best left for the research of the electric universe group.
Okay. Yeah.
Because they would be more qualified because they have a larger frame of reference.
But you think that that's an experiment that they need to
I believe that's a nexus point.
Has anybody done that, Neil? That you know of?
Well, we used to have the earliest, basically the electric universe sort of spawns. The first guy to do it would be, Benjamin Franklin, I guess. And then past him, you would go to probably, all of the electrical engineers through up till Birkeland, I would say. And Birkeland was the gentleman who was from Norway, whose we named Birkeland currents for, because he predicted that the currents coming from the sun will make the aurora on the Earth. And of course, Sidney Chapman disagreed by the way that he said that we have closed magnetic field lines of the Earth, and it's basically like a torus. And that's all it is, blah, blah, blah. You can kiss my butt. But he was the predominant dude of the day, and he got his way. And Birkeland committed suicide somewhere in 1905. But during his time that he was alive, he built Torellas, which are to study the aurora, which were basically a magnet inside of a sphere, and this sphere would have an anode in it, and it would be a vacuum chamber. And he would get to see the auroras forming along the top ring of the where they should form.
Okay.
And of course, he also made the rings of Saturn, for example, same thing, because that's exactly where they should form, and so on and so forth. So that's basically probably the closest we would get the beginning of that form.
Okay.
And there has been some reconstructions of those.
Okay. Okay. We got to, what do you guys think? Should there be a part 2 to this or not? But I want to hear.
I mean, yeah, we could talk about singularities next time and a couple other things.
Yeah. I mean,
that's one of my favorites too.
I know I was going to get to it, but
we're running up against a hard. I told you we
I
had a little bit of a hard
guys.
time on it tonight, man.
but I'm certainly willing to talk with you about it.
Neil,
definitely, and I will. I'll make a point to make sure that you can find a lot of those things I was talking about, and make sure we share it.
Oh, the
so that you
references.
Thank you.
Yep.
Well, it would only be fair, and a lot of them are simple, and they come across as scientific, and we're. Obviously the goal here, of course, is not to debate necessarily the data, but to see the underlying assumptions it's based on and to challenge them. And that's where we come from.
If you're into any ancient history, man, I'd be down to talk with that too.
That's
what my degree's in, actually.
Well, we've done a lot of trying to understand the rewriting of history, because a lot of the electric universe models would have to do with that, because let's be fair, the thing that really comes across as strong is if you have a mechanism that can move bodies around, then we don't have to relegate a lot of these things to myth. They were basically historical records of what happened and what they saw. And we call them, these reenactments, myth or silly, but I think that they were doing their best. And I think that that's why I try to give a little bit of credence to religion. They're still screaming from the past, saying something happened. Now, of course, they totally screwed up in the last 1,500 years at least, but they were really trying to be devoted to something that, and to the stars themselves.
Yep.
They were part of the heavens, and they considered themselves such. And we should be listening to them more.
Well, certainly it would be an interesting conversation.
Yeah, hell of a topic conversation. That's the thing with this theory, though, too, is that it's so multifaceted. I've heard so many different theories and opinions on different things and how it's supposed to tie together.
Psychology itself actually is a challenge. It has a few people in it that are because. One of the things is that they're starting to recognize a forgotten trauma that we've had as a species, and we pass that down in every one of our stories. We make destruction of the Earth films all the time.
Yeah, it certainly seems to be.
This is a doomsday. We are doomsday creatures,
it's
and
definitely
we have been
part
tortured
of
by something.
Of
we
the
don't know
human
what.
condition, for damn sure, isn't it? It's just all over the place.
Well, I could talk with you for hours about
that
Western apocalyptic religious sects and groups of people, the Asayans, and
it's nuts, right? We'll never run out of material.
All the Gnostic Gospels and stuff. Oh my gosh! Okay.
All right, man.
But some of the stuff is very common amongst around the world, and that alone, unless we admit that they travel around a lot, they were telling things from a different point of view from their own where they were on the Earth when they saw it, and I think that is very compelling.
I know. I know you and Sherfu have talked about that quite a bit, and these petroglyphs and stuff, and
oh my God, yes,
I love that stuff. So. All right, man, let's wrap up here. We'll figure out how we're going to do a part 2 to this. We got to get Eric out of here tonight. So thanks for listening, everyone. Check us out at www.noshitcast.com. It's KNOWSHITCAST.com. Make sure you hit those like and subscribe buttons. Leave us a comment. We'd love to hear from you. Give us
Don't forget to see the electric view either.
Yeah, right. That's true. Yeah, you got a show on YouTube. We didn't talk about that. We always talk about that, but yeah, make sure you check
that's
out.
Okay.
Yeah, no doubt. I'm sorry about that, man.
Don't worry about it. We got really carried away, and I loved it.
All right, folks, if you like what we do, give us a share. We'd really appreciate it, and we'll catch y'all next time. Thanks for listening, everybody. Bye, Sickles. Bye.